another new circuit component, which today is going to be the inductor. So with the inductor here, we'll introduce it today and we'll spend some more time with it next week on Tuesday as well, where that one will be going through and doing kind of the same thing we did on Tuesday with the capacitor. So as a reminder, with what we did for capacitors last time, is we looked at them in DC circuits. We looked at charging and discharging. And then we talked about in the AC circuit, we have this new thing called reactance. So for the reactance, in the case of a capacitor, we're going to see that as XC. It's 1 over 2 pi times the frequency of our source times the capacitance value. And so with this reactance, it's telling us how, in this case, the capacitor is going to go through and basically resist the change in the voltage across that capacitor as we go through and have time progress. Are there any questions about capacitors in circuits? So today we're going to introduce the basic inductor. We're going to talk about some different types, and we are going to talk about series and parallel inductors. Something I want to be very clear of for today, we are going to take a little bit of an aside to talk about some of the background for what is happening with inductors, because unlike resistors and capacitors, inductors are a little bit more involved with how they go through and interact with the current. So we are going to have to do a little aside for that. But the reason for that is if you go through and you look at these sources for magnetism, it turns out at the end of the day, magnetism comes from moving charges. What's a current again? It's a flow of electrons if we're talking about the electron current, or the flow of positive charges if we're doing the conventional current. Both of those are charges. They are moving throughout the circuit, which means that we have always been going through, and without talking about it, there has been magnetic fields that have been created through our circuits. Now, mathematically, a lot of the times it's not very relevant for going through and utilizing in calculations. So if we think about the circuits that we've done, again, that magnetic stuff typically is going to go through and round out and not be relevant. But when we have inductors, within the inductor portion of it, that is something that is going to be relevant. Because it turns out that inductors store energy in the form of the magnetic field. So with capacitors, they went through and they stored energy in the electric field. Inductors are going to do so with the magnetic field. So down here we have an inductor, which we'll formally define here in a second. These dashed, or these lines that are kind of going through and looping around, those are the magnetic field lines for our inductor here. Now with this particular type of inductor, this is referred to as a solenoid. So with a solenoid here, that is going to go through, and that is just a very specific type of inductor. It is going to give us specific equations that we can go through and utilize, such that what we're going to talk about today, as well as next week on Tuesday, actively applies. Because you could technically have wires that are looped, that are far apart. And with these, again, here we have our magnetic fields. Because of how they're going to go through and they are further apart, we don't have a location where we're going to have a constant value. With the solenoid, because of how the loops are close together and with how many we typically are going to be seeing, everywhere in the center of the solenoid is going to have a constant magnetic field value. So here where we have just the two loops close together, in reality, we should have multiple loops pretty close together to go through and get these nice uniform magnetic fields inside. And those are going to go through and then allow us to have the equations that we'll be talking about today. So with the solenoid, it's going to, or again, all inductors we're going to look at, they will be solenoids in this class. With it, they are going to be a little bit, and by a little bit, I mean they're fairly more involved when it comes to talking about how the inductor is going to interact with the current. So if we think about the resistor, how we had our equation for voltage via Ohm's law, where we had the voltage was equal to current times resistance. Right, just a number and a number and a number. We just had three numbers that we can go through and utilize. When we have our capacitor, again, we just have voltage, we have charge, and we have capacitance. Just going to be three numbers. Once again, the equation looks a little bit different where we have division instead of multiplication. But again, it's just three numbers. With inductors, because we still want to go through and utilize Kirchhoff's loop law, we need to go through and talk about it in terms of voltage. It is going to be different in the sense that it has a derivative in its definition. So with the equation here, we have the IND. This is the instantaneous induced voltage. So the little b telling us it's an instantaneous value, IND telling us it is induced. It is going to be equal to L, where L here is going to be our inductance value. Then we have the time derivative of our instantaneous current. So sometimes you'll see it with a capital I, sometimes you'll see it with lowercase I. It's all going to depend on whether or not we have an AC or a DC source. So our equation, two numbers, and now we have a derivative inside of it. So with this equation, it does have representation for it in a couple of different ways. Again, we'll talk about a little bit from where this comes from here shortly. But with the inductance, which is going to be L, right? Can't use I for inductance because I already belongs to current. So here we have inductance. It is a measure of a coil's ability to establish an induced voltage as a result of the change in the current. With this voltage, it is going to be the opposite in the direction to the changing current value. And we will define what that means as we go through and talk about a little bit of the physics. So with inductance, it is going to be more involved, but we'll get there. We'll talk about it. We'll do a majority of it today, and then we'll do some more parts of it on Tuesday. So any questions so far about inductors? So let's talk briefly about the other equation that we have for inductance. Because trying to calculate inductance through this, not a fun time. So we have the equation here, which is the inductance for a solenoid. So again, all of our inductors in this class will be solenoids. So we will be able to go through, and if we needed to, use this equation here. So here we have mu naught, which is the permeability of free space. It is 1.6 times 10 to the negative 6 newtons per amp squared. What this is telling us is it's going to tell us how magnetic fields behave in a material, with it being mu naught. That is explicitly how magnetic fields behave in vacuum. So we have our permeability of free space. Here we have n squared, where n is going to be our number of loops. A is our cross-sectional area of our inductor. And then L is going to be the length of our inductor. So if we go through and attempt to draw a picture here of an inductor, right, we have a bunch of different loops kind of side by side. When we're talking about the length, you're talking about how long is the inductor, so how long is the coil, not how long is the wire that makes the coil. If we hypothetically turned our inductor such that it was facing you, what shape do you think you would see? Okay. Yeah, this is typically, our inductors are typically circles, not always. I will be pulling some out next week just for fun. You can have square ones, but for the sake of this class, we'll talk about circular ones. So when I'm talking about the area, I'm talking about the area here of the circles. That is its cross-sectional area. What is the area of a circle? So for the sake of this class, we're probably going to see pi r squared here being that area value. So this is our equation. If we needed to go through and calculate inductance, I think you're doing one question on this for the homework, and then it'll show up on the conceptual part of exams moving forward. But when it comes to a problem-solving question, similar to the capacitor, typically you're going to be given that value. So let's think about all the fun names that we've had for our units. When we've been talking about our voltage, it's been in volts. When we've talked about our resistance, it was in ohms. Our capacitance has been measured in capacitance, which is in farads. With the, right, there's no rhyme or reason for what's going on, and that continues here, where the SI unit of the inductor, of the inductance, is going to be the Henry, which is represented with a capital H. And here is a short list of all the different ways you can go through and represent the Henry. The one that is important to us for the sake of this class is the volts times seconds per amps. That is going to be the one that is typically the most useful to go through and utilize. But even with just the list here, right, we also have kilograms, meters squared per second squared per amp squared. You can have joules per amp squared. If you look at the Wikipedia page, I'm pretty sure, I think it goes like all the way across the article is all the different ways you can represent the Henry. So if you just put everything into SI units and you plug it in, your answer pops out in Henry. I'm not going to stress about you knowing all of these different variants here. The last thing we need to talk about for Henry is more often than not, we are going to see millihenry and microhenry. A 1 Henry inductor is a very large inductor. We don't typically use this. So milli is 10 to the what again? And what about micro? Yep. These are going to be the most common ones that you can go through and see. Sometimes you might go all the way down to nano, but these are going to be the two most common that you'll see. Any questions so far about inductors? So with inductors, for the sake of us, again, moving forward when we're doing our inductor circuits, we're going to just be given L values, so we don't need to worry about it. But technically, there is a variation of this equation here, where it's just going to be mu. So here, the only difference is now we have mu here, where that's the permeability of that specific object. Because it turns out it's a little difficult to go through and just perfectly coil a wire about empty air. And one of the ways we can increase the inductance without increasing the size is we can put something inside of it. And so when we put something inside of our inductor, that is going to change how that magnetic field behaves a little bit. So we have mu here for the permeability of that object. Something we just want to be careful of. So let's say hypothetically you are looking up a value for the permeability of free space. We want to make sure that we're not accidentally looking up the permeativity of free space. Very similar sounding words, very similar looking words. One is for electric fields, one is for magnetic fields. So just be careful if you are looking up a value. With a lot of the values that you might see for inductors, a lot of the times they like to put a metal inside of the inductor. So replacing this, right? So here it's with the core material. More often than not, it is a metal. With the wire, we are assuming it is insulated from being physically in contact with that core. If it's physically in contact, we have a short. That is a problem. That's not an inductor. So there's some type of isolation between the wire and the core. And with these cores, the most common ones that you can see, you have iron, you'll have cobalt, or you have some metal alloy. And unlike with capacitors, those values are typically given to you in these questions for the textbook. So it will give you mu to go through and utilize. We'll talk a little bit symbol-wise, what it looks like when we have a core in a few slides here. But are there any questions so far about inductors? Just really quick, I don't think this equation is gonna pop up very much in this class. If I pop up much, I mean at all outside of today. But energy storage, we have 1/2 inductance times the current squared. With this, right, it's just a way to go through and show that energy is being stored. It is dependent on what is the current passing through, as well as the inductance value. With what we'll see next week, the inductor not as good as storing energy as the capacitor. So this equation is typically less useful than its counterpart. So let's think back to what is one of the major assumptions we have utilized all throughout this class associated with wires. What did that mean to us that they were ideal? Okay. Yeah, there were no heat loss into the environment. And what else about them? What was their resistance value? Our resistance value was 0. So it turns out for inductors, not the best way to go through and represent them. Technically, right, because wires do have resistance. If we had an inductor, which is just a lovely coil of a bunch of wire, there's a bunch of resistance inside of that coil. So this gives rise to what is referred to as the winding resistance, which has to do with winding your wire. And typically with its representation, we don't want to combine two different types of circuit components into the same circuit component. So what you go through and do instead is you pull out that resistance. So now we have a resistor that is associated with the resistance for our particular wire. And it's typically a pretty small value. So even though this is going through and looking more at a more realistic inductor, we are still going to be going through looking at ideal wires and not technically considering it. But if we wanted to be super accurate, we should go through and do so. We are not getting super far into all of the weird things that you can do with inductors in this class. Because it turns out that with our inductors, because of how we go through and have our coils, it kind of looks like a bunch of little parallel plate capacitors. Which again, we don't typically like to go through and have them be combined into, right, the same circuit component. So if we were going through and looking at this ideal inductor, we would technically have to go through and do something like this. We're not going to do it for this class. We are going to be looking at the simplest cases for inductors. If you go on to take circuits 2, you will get to go through and learn about inductor polarity, how that affects different parts of the circuits, and go through and deal with that then, but we're not doing it in this class. So if we need to include the winding capacitance and the winding resistance, every inductor would need to be represented like this. We would have a resistor, a capacitor, and inductor in series, and it would be in parallel with a parallel plate capacitor, in which all the equations we would look at today would not work. So again, we are not going to be doing this. But we do just want to understand that we are still looking at ideal circuit components. So we'll be able to ignore the winding capacitance. We'll be able to ignore the winding resistance, and we will just have an inductor. Please understand that if you're doing real circuits with a lot of inductors, it will get worse. We're just going to leave it there for now. So we're going to talk a little bit about the why there is a time derivative in our definition for voltage. And for doing that, we are going to talk about Lenz's law. Now, for the sake of Lenz's law, in this class, we are not going to care about all of the different things that it does. For the lab next week, I will pull out some inductors, I'll pull out some magnets, and we can go through and see these results, or kind of see this, but it's not super important. However, I want to understand why we have the equation that we do, to understand how it's going to work inside of our circuits, and how we're going to get shorts versus breaks and all those fun different things. So in this textbook, it is first introduced in chapter 10, where it first gets mentioned. And if we go through and look at what Lenz's law tells us, Lenz's law says that a changing magnetic field will create a current. That is going to create a current. And that current is typically referred to as the induced current. But this is weird, because if we think about at the beginning of class today, we said that magnetic fields magnetic fields are created by moving charges. So now if I have an induced current, I have induced motion of charge. So by having an induced current, I am going to create an induced magnetic field. Oops. So now I have two magnetic fields. I have the one that's created by, I have a changing magnetic field, which created a current, which now is also changing that magnetic field. So now I have two magnetic fields interacting with each other. And as those interact with each other, the magnetic field is changing. And because the magnetic field is changing, so too is my current. And I have a changing current. And because I have a changing current, I have a changing magnetic field, and it's going to go through and it's going to feed itself. So this is especially important when we have an AC source, and we're going to constantly be changing the current that's being applied into our inductor. Because the current's constantly changing, that magnetic field would constantly be changing, and the induced current that it creates is constantly changing, which is constantly going through and interfering with itself. So this is what's happening inside of our inductor, not all the time, but rather often. And so what this is going to go through and do is it means that we are going to constantly be having changing currents as we go through and look at our inductors inside of a source. So this is kind of what's going on with that. So while we have that changing current, right? Because we have the time derivative in there, that means that the voltage value is constantly going to be changing. So for an inductor, current and voltage are changing together as we go through and interact with everything. So we're going to look at some pictures for a circuit as it goes through and has this changing behavior. I am not super concerned with you guys coming out of this knowing everything about Lenz's law. Again, we're going through and talking about this such that when we get into our stuff on Tuesday, we better understand why we're seeing the behaviors that we are seeing. But if you have questions, please do feel free to ask. We're going through and doing this because we have some time today. Otherwise, I can talk about Lenz's law for like hours. I think it's cool. So let's say this is our circuit here. With our circuit, we have a battery source here. We have an ammeter. We have our inductor. So we'll talk about the symbol formally for a little bit, but it's just a little squiggly. And then we have two resistors. Resistor 1 is always kind of connected into our circuit. And then we have a switch opening and closing for resistor 2. So with this particular circuit, we are going through and it has a value that's being given by the battery. It's just outputting some amount of current. And if I close this here, so let's talk about it with it open. With it open, which resistor or resistors are important? Why? Yeah, no current to R2, so it's not important. What about if I close the switch? R2 now important. Why? Yeah, now I can have current flowing through it. And because if I think about my resistors in parallel, right, if I have R1 and R2 in parallel, when I combine them into an equivalent resistance or a total resistance value, that value is less. Which means that if I was to go through and close this, I'm going to start seeing some interesting behaviors. So for this diagram here, we are assuming we have just closed the switch. And so now the current that is passing through, I have current 1 and current 2. I now have these two currents I would need to go through and consider. I now have an ink. If I look at my diagram for the magnetic field, what these arrows here are representing is I'm having an increased amount of magnetic field inside of my circuit. And so because I have this changing magnetic field, I now have a change in the current that I am going to be seeing. So this is going to be going through and influencing the total current inside of my circuit. Depending on exactly what's going on in the circuit will determine on whether or not that current is going to increase or decrease. In this particular case, because I have that second path, it is going to increase. We're assuming we're increasing it, and I haven't we'll see equations next week, but it's going to be an exponential change to my current. And eventually what's going to happen is as I go through and have this run for a long period of time, eventually things are going to end up being constant. So eventually what's going to happen is the inductor's induced current is going to start to balance out over long periods of time. So we'll talk about a new time constant. And then we're going to have the two values added together being some constant value. If we're thinking about, right, going through and starting to figure out voltage, I would need to look at DI over DT. If my I1 plus my I2 is constant, what would my time derivative be? What's the time derivative of a constant value? So now, if enough time has passed, I'm still going to be storing energy inside of my inductor. But because the time derivative of the current is 0, the voltage across the inductor is now 0. And when we have a voltage being equal to 0, we can treat it like what? Short or a break? A break has infinite. Yeah, so if enough time passes, an inductor behaves like a short. Oops. Oh. So an inductor is going to be a little bit weird. When you first change something with a circuit, it's going to have infinite, in quotes, not really infinite, amounts of resistance, so it looks like a break. And then after long periods of time, it looks like a short. So it's a little bit backwards, kind of for what's going on with the parallel plate capacitor. You can keep going with now, if you open the switch, what's going to happen is now the current is going to change. And then over time, the energy stored in that inductor is going to be changed as well. In this particular case, it will decrease over time. So we just want to understand that with, again, I'm not expecting you guys to be experts in lenses law. Just want you to understand that changing current is responsible for the voltage, which means that we will have to look at it at specific instances in time. That is more so going to be our focus next week, Tuesday. But are there any just quickish questions about lenses law? Okay, so let's talk about symbols inside of our circuits. There's a couple different types of inductors. So you have what is referred to as the fixed inductor. So this is just a numerical value, whatever it happens to be. For the sake of drawing, if I'm being honest, I always draw mine the opposite direction. Mine look a little bit like this, but as long as they're loopy, I don't care. So inductors are loopy, resistors are spiky, capacitors are two straight lines. I don't care how perfect they are. For a variable inductor, depending on the exact device itself, what you might have happen is, and we'll talk about series here on the next slide, you'll go through and maybe you'll add some length to the inductor. You could have variable with a ferrite core, where ferrite is an iron-based material. So it won't be pure iron, it'll be something iron alloy related. You can have what is referred to as the air core. So, right, same symbol as fixed, but now you're supposed to know that there's air inside of it. Don't ask me how to make these symbols. I agree that it should be a curly, squiggle, but that's about it. If you see air core mentioned, due to the nice approximations that exist. The permeability of air is approximately the permeability of free space. And by approximately, I think it shows up in the 10,000th place where they start being different. So typically, you just use vacuum if you have an air core one. The other most kind of common one is the iron core. So that's straight lines above it. If we're being 100% honest, I only care about two of these. And that's going to be these two. I don't care about all the other fun symbols. And in reality, these are the same to me. So just draw a squiggly. Again, it doesn't have to be perfect. So we have our, right, fixed variable, fixed with ferrite, air core, iron core, ferrite core. And I did not make these symbols, but there are also ones for different types of alloys as well. It's a mess. Just draw a little loop-de-loop. That is enough. Please draw more than one loop though. Symbol wise, it is typically 3, but if you draw 2, that's fine. If you draw more, that's fine. But try to really show that it is a loop. And we want to understand that it's a solenoid. So multiple loops, so you should draw 2. 2 or more. That's all I'm looking for drawing inductors. So we're going to go through and we're going to talk about inductors in series and in parallel. But before we do that, any questions so far? So for resistors in series, what was the same? Okay. What about for capacitors in series? Wasn't current, it was something else related to current. Charge. It is the charge. So let's think about our equation here for inductance. And here we have a picture of our many inductors in series. So let's look at this equation, right? I've got mu, so here we're assuming we don't know what type of inductors these are. They can have something in them, they cannot, who cares? I have n squared, I have a, and I have divided by L. If this is ideal, what do we know about these wires? They have no resistance. So what's stopping me from taking them and start shoving them and making it one really long inductor? Picture-wise, absolutely nothing. In practicality, maybe we don't have the ability to shove all of our inductors into one long coil, but we can treat it as if we were just increasing that length. Here we are making the assumption that we do have the same area for all of our inductors. We are making an assumption that area is the same. If area is different, technically, it's going to look a tiny bit different for combining them together, mathematically. So, right, we're increasing the number of coils, so N goes up, L goes up, but N is squared, so that goes up better. What do we think is the same for these? And why? Got 2 options, current and voltage. Which one's the same for all these inductors? Yep, it's gonna be the current. And that means that we can go through And we can have the total inductance being just, we add all those inductor values together. Which equation does this look like? Does this look like total resistance or total capacitance? Yeah, matches the resistance. If we go through and look at our equation for the voltage, right, we have V is equal to L dI over dt. If we think about the voltage for the resistor, that was V is equal to IR. So here, yes, it is a little bit more complicated because it's not I, it's di dt. But it's formatted the same. The way we sum those up together is going to be the same. So based off of that, what do you think happens when they're in parallel? What's the same? Gonna be voltage. And what equation do we think the total inductance is gonna look like? Resistors or capacitors? Yep. Oops. So it looks the same as a resistor. Because they're different circuit components, they do have different equations, but the behaviors are the same. Kirchhoff's loop law still applies, and we still get to go through, and the voltage needs to be the same if they're all in parallel with each other. So in this case, right, B is the same. Whether that's right instantaneous or overall, it is going to be the same with them each time. All right, any questions before we do some total inductance calculations? All right, so what would we do here for 18A to find LT? How do you know L1 and L2 are in parallel?
Picture.
Yeah, they have this, right, the same starting and ending junctions here. All right, what do I do next?
What oil?
Can't forget to take that inverse value there. Yeah, 3 and 4 are in parallel. We do that combination, that's now in series. Do I need to worry about conversions for A here? Why not? Yeah, they're all in millihenry, so I don't need to go through and worry about it. So we can just plug that in and go. So we'll have 1 over 100 millihenry plus 1 over 50 millihenry. Right, that gets inverse plus 1 over 60 millihenry plus 1 over 40 millihenry inversed. Assuming I plug that in correctly, I got 57.333 repeating millihenry. Or if we wanted to round, but technically it's a 2 sig fit question here, 57 millihenry. Any questions on A? What do we do for B? Okay. All right, yeah, so 1 and 2 are in series, 3 and 4 are in series, and what are they with respect to each other? Yep. So if we wanted to do it all at once, you'd have 1 over L1. Sorry, I keep picking up my hand funny. Plus 1 over L2, plus 1 over L3 plus L4, and all of that gets inversed. Do I need to worry about units in this one? Nope, same. These are all also in millihenry. So we can just start going through and plugging those in. It is okay, as long as you are aware of what the units are, especially when you're going through and summing these together, to just add the values. So you could do your 8 plus 4 plus 1 over 2 plus 4 inversed. No, all the values are going in are millihenry. So our answer is going to pop out in millihenry. And this one happens to be, again, assuming I plugged that in correctly, exactly 4.0 millihenry. Any questions on B? So how would we do C?
See with 3, 4, and all 4 of those are parallel, and I'll get that in series with
Mm-hmm. Yep, so L1 is in series. Yeah, so L1 is in series with oops, this ugly mess of a thing over here. Maybe. Yeah, so I'll have 1 over L3 plus L4 plus 1 over L2 plus L5 inversed. Do I need to worry about units? Why not? All in millihenry, so we can just go through and again, not stress about the units for that. So I'll have 4 plus 1 over 1 plus 1 plus 1 over 2 plus 2 inverse, which assuming I plugged that in correctly, I got 5.333 repeating millihenry or 5.3 millihenry. Any questions about inductors and series and or parallel? So next week we will go through and we'll start combining it with the resistor. And we'll talk about them in DC and AC circuits. See you guys next time.